In this video, we're going to talk about Lagrange error bound. So when we have f of x will equal to p sub n of x, which is the nth degree Taylor polynomial, plus the remainder. So f of x represents the exact value, and p sub n of x is the approximate value. By the way, the higher the n gets, the approximate gets closer to the exact value. Using this equation, we could say that r sub n of x is f of x minus p sub n of x. And note that when we make approximation, it will give us an error. So the error turns out to be the absolute value of r sub n of x, which is going to be the absolute value of f of x minus p sub n of x. And note that these two are the same thing. Since these two are inside the absolute value, even though you change the order, they have the same value. So we have f of x equals f of c plus f prime of c times x minus c plus so forth. Note that this is the formula for Taylor series as center as c, and then plus r of n of x, which represents the remainder, where r sub n of x is equal to f of n plus 1 derivative of z over quantity n plus 1 factorial times the quantity x minus c to the power of n plus 1. So this looks like the term that follows after this. And this r sub n of x, we call it the Lagrange remainder. So here c represents the center and n represents the degree of the Taylor polynomial, and x represents a number that you want to approximate. And the most confusing part of Lagrange error bound is the letter z. What is z? A z is a number between c and x, the center and the number that you want to approximate. And it turns out that our maximum error is at most the absolute value of Lagrange remainder. And in order for this to happen, what we need to do is we need to find the maximum value of f of n plus 1 derivative of z in order for us to get the maximum error. Again, in order to have a maximum error, f to the n plus 1 derivative of z should be maximum. In other words, this value should be the largest as possible. So let's take a look at this example. It says the third Maclaurin polynomial for sine of x is given by p sub 3 of x equals x minus x cubed over 3 factorial. Use Taylor polynomial to approximate sine of 0.1 using p sub 3 of 0.1 and determine the accuracy of the approximation. Now p sub 0.1 is, instead of x, we need to substitute 0.1. If they don't let you use calculator, you could just stop right here. But if they let you use graphing calculator, you probably want to evaluate this and give them 0.099833. So this is the approximation of sine of 0.1. And they want us to determine the accuracy of this approximation. In other words, we need to find the maximum error of this approximation compared to the actual value of sine of 0.1. So let's write down the given information. We have f of x equals sine of x. And since this is the Maclaurin polynomial, we know that the center is at 0. And this is the third degree polynomial. So n equals 3. And the value, the x value that we want to approximate was 0.1. So our x is 0.1. Now z is a number between the center and x. So z is a number between 0 and 0.1. So now we need to use Lagrange error remainder to find the maximum error. So now, these are pretty straightforward. However, finding f to the n plus 1 derivative of z is not so simple. So in order to find this part right here, we need to find, what was n? N is 3, the fourth derivative of f of x. So taking the derivative, and then we found that the fourth derivative of sine of x is sine of x. Now remember, recall that we said that you want this value to be the maximum or largest possible in order for us to have a maximum error. So let's look at the interval. You want the value of z, which is between 0 and 0.1. You want the fourth derivative of f of z to be the maximum. So take a look at this. The fourth derivative is sine of x. And sine of x looks like this when you graph it. From 0 to pi over 2. Now let's look at the interval. Z has to be between 0 and 0.1, which is about here. And what is sine of pi over 2? Sine of pi over 2 is 1. So 0.1 is about here. Now, which value of z? Now, you know that since sine x is increasing, sine of 0.1 will give you the maximum value. By the way, whenever the function is increasing, the right-hand point will give you the maximum value. And if the function is decreasing, then the left-hand point will give you the maximum value. So in this case, since sine of x is increasing function, the right-hand point, sine of 0.1, would give you the maximum value. But we don't really know what that value is unless we use our calculator. But the whole point of doing this is so that we don't use calculator. So we're going to safely say the maximum value that this will be is 1. Now, by plugging in our values, you get the maximum error is the absolute value of f of fourth derivative of z times the quantity 0.1 to the fourth power over 4 factorial. Since x equals 0.1, center is 0, you get 0.1 over here. Now, we just talked about what should be our maximum value of this, f to the fourth derivative of z. This is 1. Since that's 1, you get quantity 0.1 to the 4 power over 4 factorial, which is the same thing as 1 over 4 factorial times 0.1 is the same thing as 1 over 10, and quantity 1 over 10 to the 4th power. Now, this is as far as you could go without the graphing calculator. Now, in decimals, this is approximately 0.000004. So our approximation was pretty close to the actual value based on this Lagrange error remainder. Now, suppose we use the first two terms of the Maclaurin series for f of x equals natural log of quantity 1 plus x to approximate f of 0.1. Find a bound on the error by using the Lagrange error remainder. Sometimes the word remainder, some books, they use a formula. So in order to find the first two terms of the Maclaurin series, I took the derivative up to f triple prime. And we'll see if this is enough to find the first two terms. So plugging in 0, since the Maclaurin series has a center of 0, you get f of 0 is natural log of 1, which is 0. and f prime of 0 is 1, and f double prime of 0 is negative 1. And since they wanted to use the first two terms, and the first term came out to be 0, I need to go up to a second degree, which means n equals 2. So I get this as my second degree Taylor polynomial. So our approximation is going to be 0.095. Now, what will be our error, maximum error of this approximation compared to the actual value? So we need to use Lagrange error remainder, and let's find the necessary information we need to evaluate this. So we know that the center is at 0, and n turns out to be 2 because we went up to second degree of the polynomial, and x is at 0.1, and z is a number that is between the center and x value. So z is any number between 0 and 0.1 that will give you the maximum value of this. So that means we need to find the maximum value of third derivative of f of z. And you know that the third derivative of x is this right here. And this function is a decreasing function. And how do we know that this is a decreasing function from 0 to 0.1? Well, take the derivative of that. When you take the derivative of this, you get negative 6 quantity 1 plus x to the power of negative 4, which is the same thing as this. The fourth derivative will be this right here, which is a derivative of the third derivative. And notice, the derivative of this is always negative, especially when x is from 0 to 0.1. Since the third derivative is always negative, you could tell that this is a decreasing function. And since f triple prime of x is a decreasing function, you know that the interval from 0 to 0.1, the maximum will happen at 0. So our maximum value of this will happen at the left-hand point, since the function is decreasing. So what is f triple prime of 0? It's going to be 2. So now we get this setup over here. So now we just talked about f to the third derivative of z will have a maximum value at the left-hand point, and the value of the maximum value of that will be 2. So you get 2 times the quantity 0.1 to the third over 3 factorial, which is 1 over 3 times 1 over 10 to the third power. So this is the maximum error of the approximation compared to the actual value. Suppose the second order Taylor polynomial for f of x about x equals 2 is used as an approximation for f of x. And suppose that absolute value of f to the third derivative of x is less than 2.3 for all x in the interval from 2 to 2.5. Show that the absolute value of f of x minus p sub 2 of x is less than 0.05 for all x in the interval from 2 to 2.5. So basically this here represents the maximum error caused by the approximation. So from the given information, we know that the center is at 2, and the n is equal to 2. Also, we know that it's 2 because it says the second order Taylor polynomial. And the x is 2.5 because look at the interval. It's going from the center to the value of x. So x equals 2.5. And the z is any number between 2 and 2.5. This information will be crucial later on when we find the maximum error. So we have a maximum error as absolute value of this. Now let's plug in the values, and we get 0.5 over here because 2.5 minus 2, and then we get 3 factorial on the bottom. Now check this out. What should be our maximum value of f to the third derivative of z so that we'll have a maximum error? Well, according to given information, check this out. The absolute value of f to the third derivative of x is going to be less than 2.3. So the maximum value of this is 2.3. So therefore, you get 2.3 times 1 over 3 factorial, which is 1 over 6. And then quantity 0.5 cubed is the same thing as 1 over 2 to the third power, which is 2.3 times 1 over 48. And 2.3 over 48 is less than 0.05. So we just showed that the maximum error is less than 0.05.